Okay, hello everyone. This is chapter 23. In this chapter, we are going to cover electric fields of a continuous charge distribution, electric flux, Gauss law, and some application on Gauss law. Again, as a reminder, please write this. Okay. So before I start, let me take you a little bit back to what we covered in the previous chapter, and I try to connect it to the topic of this chapter. So in the previous chapter, one of the last topic that we discussed was finding electric field from a point charge or several point charge. So if you have a point charge, let's say positive Q, and we wanted to find electric field at a point P, what we do, we assume there is a test charge located at point P, and we try to find electric field from originated or produced by this positive charge. So if you put the test charge at point P, the electric field will be this direction, and the value of the electric field is simply depending on the value of this Q. This is the source charge, and also the distance between Q and point P. So that distance, let's say R. The value of the electric field simply is equal to K Q divided by R squared. Now, if you have another point charge, for example, here, let's say minus Q, the minus Q will also produce electric field at point P that will be directed toward it. So let's say this distance R1 and this distance R2. So now you have another electric field. So if this charge is Q1, this charge is Q2, this will be E2, this will be E1, right? So this is E1, E2 would be equal to K, Q2, R2 squared. Okay, so now you have two vectors. You know how to deal with it. We went through many questions before. Simply two vectors. So in this case, each vector will have x component, y component, and you could deal with summation of the x component. You find summation of x component and summation of y component, and you proceed. And if you remember, I said this method is only applicable if you have point charge, if Q1 and Q2 are point charge. But what if you have a continuous of charge distribution? Means instead of a point charge, what if the charge was distributed over a ring or a disc or a cylinder or maybe a rod? In this case, we can use that equation because this is for a point charge. Q1 and Q2 were point charges. Point charge. So we need to use some trick, some method in order to get into the answer. And of course, integration will be involved. So here the task, here the new task. So electric field continues from continuous charge distribution. Note the previous method that we just described, we just discussed, for finding electric field only works for point charge. What if you have a distribution of charge like this irregular shape? It's charge with a, let's say, charge Q. Well, we cannot use the equation I just described. In this case, what we do, we will divide this charge into many small pieces. Each one represent, or each one carry a small amount of charge, delta Q1, delta Q2, delta Q3, delta Q million. You have to have many pieces there. And then the task is, let's say you want to find electric field at point P. Well, electric field at point P, if you want to find it, you assume there is a test charge located there. So assumption here, let's assume that Q is positive. So for example, Q1 will produce electric field at P given by this vector. Q2 will produce electric field given by this vector, and Q3 will produce electric field given by this vector. So each of these points represent a point charge. Point So for that small point, I could use the equation I just described. So the equation for the electric field produced by delta Q1, delta Q2, or delta Q3 simply is equal to K multiplied by delta Q divided by R squared, and then this is going to give me the value of the electric field. Because the Q is delta Q, I'm going to write the electric field produced by it simply delta E. If I want to make this one a vector, so I'm going to put arrow here, and I need to put the unit vector here. Notice the unit vector, delta E has its own unit vector, delta E2 has its own unit vector, and delta E3 has its own unit vector because they direct at different directions. So now the task is you need to add all those delta E's. And the way you add it, you need to think about vector addition. And when we add vectors, okay, when you add all these vectors in a vector notation or vector summation, you will get a total electric field at point P. And the total electric field, because they all these terms, they all contain K, so K will come out from the integration, summation. So this is just summation. And you know, you could easily go from summation to integration by taking a limit. So if I take a limit and I assume that delta Q is, delta means change, right? It's approaching zero, means delta Q, instead of think about like a cube, think about like a point. So there is no dimension for a point. So delta Q is equal to 0. If you take this limit, our equation is simply going to change into an integration form. You will see some similarity between this equation and the one that used for point charge. The only difference is, of course, there is integration, and also there is this dq here. Now the question is how we could apply this. Well, in order to apply, we always bring the concept of charge density. And we do have three charge densities. We have linear charge density, which is we're going to call lambda. We have surface or area charge density, we're going to call it sigma. And we have volume charge density, we will call it rho. So this is lambda, the B is silent, lambda. The second one is sigma, the old Greek alphabet, and this is rho. So lambda is charge divided by length, sigma is charge divided by area, rho is charge divided by volume. Now, how we know which one we should use? Well, depend on the question. If the question was one dimension, we will use lambda. If the question is two dimension, we will use sigma. If three dimension, we will see rho. So let's go to the next slide and try to explain this more. So this is our equation again. And we have this dq. This dq, in order to apply, the whole equation, what we do, we use density. So we have three kinds of density. This is first one, second one, third one. In the first one, volume charge density is rho, is equal to Q divided by the volume of the object that's given in the problem. Or it's given, usually if we just described, if the charge is distributed over volume, we need to divide the volume into many, many small volumes. Each small volume will carry a charge dq, and that small volume will be dv. So rho is equal to q divided by v, and also is equal to dq divided by dv, which in this case dq simply equal to dv multiplied by rho. So if you have a three-dimensional problem and you want to solve it, most probably you need to use dq into that equation. Another case, if you have a two-dimensional problem, you will introduce surface charge density. Surface charge density is sigma, it's just a symbol sigma, is equal to q, total charge of the object, divided by total area of the object, or is equal to, usually what you do, think about the disk. a disk is a two-dimensional case, right? A disk with no thickness. So in this case, a disk is charged. You will divide the disk into many, many small areas. Each small area called dA, and each small area will carry a charge dq. So in this case, dq will be equal to this value, or dA multiplied by sigma. So now if you have a two-dimensional problem, most probably, not always, we will discuss this, you need to use this. In the one-dimensional case, one-dimensional, think about like a hair or a rod with no thickness, very long rod, or it doesn't matter long or short, a rod with no thickness, and is charged. So in this case, the density, the charge density of the rod simply is equal to lambda, it's just a symbol lambda, total Q of the rod divided by, I think this is a mistake, it's not A, it should be L. I'm going to correct this on my PowerPoint, L. So it's equal to dq divided by dl. Okay. So in that case, dq is equal to lambda multiplied by L. So when you have one-dimensional case, most probably you're going to use this. After you substitute this into the equation, you need to figure out the integration from where you took the first piece, the first division, to where the pieces will finish. So this will be clear by some examples. Okay, so I'm going to give an example in one dimension and then two dimension and so on. This is our first example. We are trying to find the electric field due to a charged rod. A rod of length L has a uniform positive charge per unit length. Means it's charged in positive charge. And a total charge of Q. Calculate the electric field at point P, this is point P, that's located along the long axis of the rod and a distance A from one end. So a few things. First, the rod is one dimensional, doesn't have any thickness. Think about like a hair, just human hair, very long or very short, doesn't matter, and it's charged with positive charge. First question we will ask ourselves, is the rod point charge? The answer is definitely no. It's a distribution of charge. So we need to use integration. The trick is we will divide the rod into many, many small pieces. So this is the first piece, this is the second, this is the last piece. So this is one of the pieces that we will use it to explain things. So we know that the first piece has a location and the last piece has a location. The origin is located here. So the first piece location has X, right? So it has X. The last piece, when I say it has X, I mean it's away from the origin by X. This one is away from the origin by X. But X for the first location is equal to A. So here is equal to A. Here the X for the last location, I should say for the last piece, is equal to what? To L plus A, or A plus L. But let's take another small piece, small element, not at the beginning, not at the end. Let's take this small piece here. That small piece definitely will carry, if the whole charge is Q, that small piece will be dQ. And it has a the length of dl, I'm going to call it dx because I have this called x, means this will be a baby x or dx. And that piece is away from the point P by a distance r, but we're going to call it x because we call this axis x. Okay. So the task is, let's find the electric field from dq at point P. Well, dq is positive. So it will make an electric field at point P that directed this way. This is dE. I call it dE because it's produced by dQ. So it's simply dE is equal to K dQ divided by r squared, but our r here is x squared. Okay. Now this is one-dimensional problem, so we gotta use a density concept to write dQ instead of density. we just described, we said lambda is actually equal to dq divided by dl, or dl is dx, right? So instead of dq, I'm going to say dE is equal to k lambda dx divided by x squared. Okay, so this is for one piece, but what about the other pieces? You have a million other elements. Well, you have to add all this. It means simply you do integration. Now, you know, in integration, the integration of dE is simply gonna give us E. For integration, you know from calculus, if you have any constant, you simply kick it out from the integration or the integral. So k is constant. And lambda is constant because the question says a uniform, I mean constant lambda. So I'm going to simply take it out. The integration is equal to dx x squared. Now, from where I should go to where? X. Where is the location of the first piece? It's A. Where is the location of the last piece? Is A plus L. A plus L. Now the task became easy. Is equal to minus 1 over x, which is equal to k lambda minus 1 over x squared, x, so we have a plus L. Now you have minus minus, so it's plus 1 over a. Okay. You calculate the electric field due to the ring at a distance p lying at a distance x from its center and along the central axis perpendicular to the plane of the ring. First, let's understand what the question asks for. Okay, so here a ring. Exactly on the screen of the laptop, there is a ring. The ring is one dimension. It's carry a charge Q. It has a radius A. The question asks you to find the electric field just in front of the center. Assume that your eye, you are watching this PowerPoint, you are watching this screen. Okay, so your eye is exactly, you know, at the center or in front of this point. So it's in front of. The ring is located on the screen while you are located outside of the screen. That's where you want to find electric field. It's point P. In 2 dimensions, you could maybe think about it this way. Again, this is a one-dimensional problem. You divide the ring into many, many small pieces. This is one piece, this is second, this is third, this is fourth, this is million, and so on. For one small piece, it's gonna carry a charge dq, and it has a small length of ds. And if you think about this is a ring, so the length will be like this, like an arc, ds. Okay. Now the electric field from that small piece, because it's a small piece, it's a point charge, we could say it simply create an electric field that goes this direction. Now if we define this our x-axis, that electric field has 2 components. One goes forward, one goes into this direction. Now before we proceed, there is a symmetry in this shape. Means that small piece, that element has another element is like a twin of it. It's this one. So what about this? The electric field from point 2 will direct this way. And we'll have also 2 components. One forward, like the other one, and one, let's say, upward here. So this component will cancel that. Now you could proceed, you could say, what about this? Well, this one has also electric field at point P. It has 2 components, that electric field. That piece has another piece located on the other side. So what you see from symmetry that all the component that we call it DE vertical, all of them will cancel out because all of them will be against each other. It will cancel out. So in two-dimensional, if you put your eye here, if you look at this problem here from there, you will see something like this. This is all this component. I'm now speaking about DE perpendicular. DE perpendicular. You have million of those opposite to each other. They will cancel out. So your task simply is to find all the DEX. That's what you want to find. So you have million of those. Okay, so what about DEX? Well, DEX is simply equal to K dq divided by r squared, but multiplied by cosine. Which cosine? Well, this is angle theta. Now we need this angle. So DEX simply is equal to DE multiplied by cosine theta. This is simply DE. But cosine theta is equal to x divided by r. So let's see, where is x, where is r? Where cosine theta is equal to x divided by r. But we don't have r, but we have a and x given in the question, so it's equal to x divided by this. Okay. Now, if you substitute this into cosine theta, our dx will be something like this. Now, a few questions we need to ask ourselves. This is only electric field, actually one component of the electric field produced by that small piece. So what about others? We just do integration. You do integration here, you do integration there. Integration of the left-hand side is simply going to give us EX. Integration of the right-hand side, let's think about it. Now, do you have any constant from this? Yes, K is constant. Actually, X is constant, right? Because this point P is staying there. It's not moving, so X is constant. So you take out X, A constant, yes, because the ring has, you know, it's a radius of the ring. So this is all constant. Constant. Now you end up having integration of dq. So now you have two methods. One of them is very, very easy. What's integration of dq? Integration of dq is simply q. This is method one. Method two, you could use lambda to get this, right? You could find lambda, but it's up to you. You want to go the lengthy way, you want to go the easy way. So if you go in the easy method, just dq is equal to q. That's it. You get the final answer. But I just want to give you the lengthy way as well, so you know what, you know, it's some practice. Okay, so let's get rid of this. Eraser, where is eraser? Eraser, because I need some space. And pointer, pen. Okay, method two. So for method two, integration of dq isn't equal to integration lambda multiplied by the length of that small piece. It's ds. But remember, that small piece, it has this lambda, right? It's like a pizza slice. That small piece, it's a very, very small piece. It's, think about the pizza slice, something like that. A slice of a pizza. This is ds, this is r, and this is d theta. This is something we have done in physics 1, right? So it's equal to integration. Lambda now I could write as lambda ds, so it's equal to lambda ds. I could write as an r d theta. Okay. Because I want to prove this equal to dq. Let's do integration, d theta. So when you take this one, this piece, this piece, this piece, all of them, theta goes from 0 to 2 pi because you are going around a ring. So it's from 0 to 2 pi. So what will be the answer? It will be lambda r 2 pi. Is this equal to q? Is this equal to q? The answer is yes. How do I know? Well, what's lambda? Lambda is equal to, I can write it as total q divided by the total length of the ring, which is 2 pi r. r 2 pi. So this will cancel out. The answer is simply Q. Okay, so anyway, here we didn't have to do this method because you already have something simple, just integration of dq. So we just got it right. Now we could ask ourselves a few questions. What's the electric field at the center of the ring? Well, at the center of the ring, well, I need to erase some of these messy things that I just made. Pointer, eraser. Okay, yeah, pointer. Yeah. At the center of the ring, this parameter is 0, right? If this is 0, what will be the answer? Simply E will be equal to K X. Oops, what's happening? Eraser. Is equal to E. So if x is 0, electric field simply is equal to 0 because you have x here, right? So no electric field over here. The second question, what's electric field at a point very far? So now x is very large compared to a. Well, if x is very large, you could cancel a, right? And the answer will be E equal to K. Now x is very large, so it's equal to x divided by x squared. Now you have x cubic. So x with x cubic will be x squared, so it's going to be equal to K Q divided by x squared, which is the same equation for a point charge, because if you are very far, the ring will appear to be a point charge. Okay. So that's the solution for that. Okay. Now this question, I'm not going to go through it, but I put a nice description. I want you to go through it carefully. This is a disk. You are using the idea of a ring to get the electric field at point P in front of the disk. So I'm not going to go through it because I have already did 2 examples. Just time doesn't permit to do every single example. But I spent some time, some effort, put explanation. I want you to go through it carefully. Okay? Okay. Try to apply Gauss law within applying on a few questions or examples. Okay? So electrical flux or electric flux is a physical quantity. Later on we will have magnetic flux. So electric flux simply is the product, is a dot product between 2 vectors. One vector is electric field and the other vector is the area. For some of you, maybe this is first time that you encounter area as a vector, but I'm going to explain this. So the symbol that used for electric flux is phi sub E. Phi sub E. Later on we will talk about magnetic flux, which will be phi sub B. But this is something we will do it maybe after midterm. Okay. So electric flux simply is the product, is the multiplication between electric field and the surface area perpendicular to this electric field. Mathematically, it's simply the dot product between 2 vectors. Electric field, we know it's a vector, but A, for maybe some of you haven't taken this topic, that A actually is a vector. So usually A is a vector, and the direction of any area. For example, let's take a surface, something like a box. This is a box. So it has a top surface. The direction of the top surface actually is going away from the surface. This is A for the top one. The direction of the side one is going to the right direction. It's perpendicular to it. This is A. and the one in front is going out of the page or out of the screen of the blackboard. Okay. So usually, or by definition, the direction of any area as a vector is given by a vector that's going away from that surface. For example, a vector of, let's say my head, top of my head is like a circle or close to a circle. So it's I could represent it by a vector, and the vector is going away from my head, upward. Okay. So in this example, we have a surface given by a area of it is equal to A, and there is electric field is pointing into that direction. Oops. This is the direction of the electric field. So in this particular case, if I want to talk about this side of the surface, so area of this side is simply with electric field, but area of the other side is in this direction. Okay. So for now, let's say we are only interested to know to calculate the flux from this side, from that side. In this case, area as a vector make an angle 0 with electric field in this particular case. So in that case will be E multiplied by A cosine 0, for example. So in this particular case equal to EA. Okay. So phi is a dot product, right? And we have done dot product relationship between two parameters in physics 1. If you remember work, the way we define work is a dot product between force and a position vector or displacement vector. So phi in this case is the angle between electric field and the area, because not always the angle is equal to 0. Angle could be anything, right, between electric field and the area. For example, let's go back to this box and let me draw it a little bit larger. Now this box has 6 sides, of course, right? Left, right, up, down, front, and the back. Okay. So let's assume that there is an electric field going in the direction of the x-axis, and let's assume this is x-axis. So there is electric field goes this way. This is electric field. Okay. Now let's try to find the flux that going through this surface. Well, flux is simply related to a number of electric field lines that are going through that. It's obviously 0. No line is going to go through that, because area here, for the top one, I'm talking about the top surface, this is area. The angle between area and electric field is 90. Cosine 90 is 0, right? Cosine 90 is 0, so there is no flux that going through the top surface. The same way, what's the flux that going through the bottom one? Again, area is downward, electric field is to the right, angle is 90. Again, it's 0. What about the front side, surface? Front surface, the area coming out from the laptop or from this screen, again, the angle is equal to 90. So there is no flux going through top surface, bottom surface, front surface, back surface. What about this surface here? Well, here, this is A. An electric field also toward it. So therefore the flux that going through this surface is equal to E A cosine 0, which is 1. So it's equal to just EA. What about that surface? The left side here. Well, here A is to the left, but E is to the right. Angle between them 180. Cosine 180 is equal to minus 1. So for that surface, the flux that going through it is negative, so it's equal to minus EA. Minus EA. What's total flux? So total flux, total, is equal to minus EA plus EA, which equals to 0. And now this result is a little bit, we're surprised by this result, but when we go into, we talk about Gauss law, it will be very obvious why it's 0, okay? Why the flux is 0. So if flux is positive and negative, they have some meaning, okay? So we will talk about these cases. Okay, coming back to dot product. You know from simple calculus, right? Cosine has the minimum value 0 and maximum value 1, which means flux could go to the maximum value, could go to the minimum value, depends on the angle. So for example, let me a little bit clean up this mess. So let's do that. I don't need this anymore now. Okay. So flux is usually goes to the maximum when the surface is perpendicular to the field. In that case, phi is equal to 0. Look at this one. Now the surface is perpendicular to the field, so don't confuse. The surface is perpendicular to the field, but the area as a vector is with the field, okay? So what about flux? When is going to be equal to 0? Well, flux is equal to 0 when the surface is parallel to the field. So for example, let's say how I draw this. Yeah, I could draw it this way. Let's say this is this. And now electric field is like that. Okay. So if this is electric field, where is area? At least for the right side of this is area. So the angle is 90. Cosine 90 is 0. So flux will be 0. No, which means no electric field lines passing through this paper. Okay. Unit, simply it's a unit of these two parameters, right? These two parameters. So the unit of it simply is equal to Newton, because electric field is Newton divided by Coulomb, and area is simply meter square. But this is like a special case, right? In general, the angle between electric field and area not always constant. So for example, in this shape, the yellow vector is the electric field direction. dA here, this is a small element, small surface. When we say surface element, means a small area. I don't know why I put this line. Eraser. That's not my intention to put a line. Pointer, pen. Okay. So the area now, the angle is simply some theta, right? What about this small area? Well, this small area, why it put this line? Eraser. Sometimes doing weird things, this pen. Okay, what about this area? Well, this area, the A is like that. Delta A is like this. But E is the same direction. Now the angle is different than this angle, which means if you go around this surface, you will find many different angles between electric field and surface element. In that case, what you do, you find the flux through one small piece. So what's the flux through that small element is equal to, because it's a small area, it's equal to E multiplied by dA multiplied by cosine theta. That's simply the flux through that small piece. So it's equal to a dot product. This is for one small piece. But you have million of that small elements, small surface elements. So you have to add. That's why we are doing summation. Now, if you take the limit of this summation, if you make the area very small, instead of showing it on the figure like this small piece, just a point, even you cannot show it like a point. In that case, the summation simply going to change into integration. Okay. So now the general definition for flux through a surface is given by this formula. Now here we put a surface because the integration or the integral has to be carried out over the area. The integration has to be carried out over the area. We will solve a few equations. Now, by notation, if you calculate the total flux, not just a portion of the area, total flux across the whole surface, instead of just putting integration like this, we're going to put integration like this. So when you saw this circle, mean you are doing integration over the whole area, the whole surface, okay? The whole surface. So for example, let me go back to the box so it's going to be easy for us to understand. If we wanted to find, in the previous example, that was electric field goes this way. If you want to calculate the total flux, you put this symbol, okay? We put this circular symbol. In that case, what you do, you are simply calculating the total flux. This is net flux or total flux. If you haven't seen this, okay, maybe now it's time to learn. This is just a notation. This is just something that we use it to represent, or integration calculation has to be carried out over the whole surface. Okay. Now, why we needed this flux definition? Because we needed to introduce Gauss law. Okay. So what's Gauss law? Gauss law simply is an equation, is a law. Simply it says the following. It says that total, because this is total electric flux, that going through a closed surface. Okay, you have a surface in space. Any surface could be any irregular shape, could be a spherical shape, could be a cylinder. We will do some example, showing this kind of shapes. So the total electric flux that going through a closed surface is equal to the value of the charge, net charge, that enclosed by this surface divided by a constant epsilon naught. So this is important. Qn is the total charge that's inside the surface, and that surface we usually call it Gaussian surface. We call it Gaussian surface. So if you take any surface, for example, if you remember the previous example, the box. The answer was 0 because, and I expected the answer is 0 because I know Gauss law, but in a few minutes you will also know Gauss law, and you should expect the answer to be 0 because this is a closed surface. Because there is no charge inside it. In the question, I never said there is a charge inside. Well, the total flux, this is total flux. It's simply equal to the right-hand side of the equation. There is no charge inside this cube, so it's 0 divided by epsilon naught, which means total flux phi E is equal to 0. Now, I need to tell you the following thing. Let me a little bit clean up this. There are two ways usually to, according to the equation of course, there are two ways to calculate the total flux. There are two ways to calculate a total flux through a surface. Total flux, I'm talking about total flux. One way is simply, this is total flux, right? Or net flux, total flux. One way is carry out the integration, which is always not a good idea. Integration we try to avoid, right? But one way is just calculate the right-hand side of the equation, which is easy. Now, what's dA here? Well, dA is a small portion, small surface element of the Gaussian surface that we're going to use it in the problem. Okay? Now, what's the usefulness of Gauss law? Well, Gauss law is very powerful. It's used to calculate electric field in problems that has symmetry cases. But before we go into this, let's be a little bit familiar with Gauss law and let's calculate some of the things. Let's try to find the total electric flux over each of the surfaces. So for example, here we have a charge, it's positive, let's call it Q. And looks like there are three surfaces, S1, S2, S3. They all, think about surface, okay? When I say surface, it's not two-dimensional. It's like a weird sphere around, irregular shape, S1, S2, S3. So the answer is simply, because Q is inside S1, and also inside S2, and also inside S3, so the total flux that going through S1 is simply is equal to that Q divided by epsilon naught. What about the phi, the total flux that going through S2? It's the same thing, because Q is also inside S1 and also is equal to the phi of the S3. Easy peasy. When you calculate the total flux, you always concern finding what charge you have inside the surface. Anything outside, you just ignore it. For example, here, the surface is this shape. It's like a cloud, this blue shape. This blue shape. And there is a charge outside it. So what's the flux, total flux through that shape? Well, let's call the shape S, is equal to 0. How do I know? Because is equal to, do you have any Q inside it? 0. No, Q is outside, divide by epsilon naught. This is one way to think about it. But there is also another smart way to think about this. Remember, this is the shape, okay? Think about like a three-dimensional shape. Here, line goes in. Means electric field line goes in. So this guy goes in, but here lines goes out. So the number of lines that goes in is equal to the number of lines that goes out. Means because total flux or flux related to the number of lines that going through a surface. Okay, so the total number of lines is like a traffic light. Number of cars approaching traffic light is equal to the number of cars that, leaving the traffic light. Okay, I have no idea why it does this weird lines. Okay, let's talk about the other example. This surface has no charge inside it, so there is no electric field line goes in or leaving. So this is simply equal to 0, because it's equal to no charge, no Q here. So no charge, so 0 divided by epsilon naught. What about here? Well, this is easy. Phi through this surface is equal to a charge, but our charge is negative, so we need to put a negative value. Divide by epsilon naught. Divide by epsilon naught. Now, here it's important. What does the negative mean? Well, it means that line of electric field actually entering the surface from all sides. Remember, because this is negative, so line of the electric field goes toward it, okay? You remember that. What about this? By the way, this is outside, so this is, we simply ignore it. We ignore this. Sorry, you are outside of the circle. What about this? Well, the total flux through this surface is equal to total Q inside. How much Q we have? We have plus Q2 and minus Q3 is equal to epsilon. Now, if these two charges were equal, they're going to cancel everything. But if one of them is larger, depending, so you might have positive flux, you might have negative flux. Positive flux means more number of lines going outside compared to number of lines going inside. Okay, so this is simply information about flux. Okay, we need to apply Gauss law. So this is our equation of Gauss law. It's important, please. I'm repeating many times. I'm repeating things. This is Gauss law. I over and over see students writing Gauss law in exam in a very weird way. For example, this is wrong if you write Gauss law like this, because you forgot this term, or people write it this way. Q divide, because you forgot the dot product. Okay, so you need to write it as is, because we are not the one that putting this law. This is Gauss law. Left hand side is equal to the right hand side. Now, unfortunately, Gauss law is not good for every single case. It's only good whenever the question has some symmetry. So we will do our best to choose a Gaussian surface because remember, this is a small element of the Gaussian surface. We always make choice of the Gaussian surface to make our life easier. I mean, to make this integration easier. Okay? So, in calculation, we always make sure that one or more of these conditions are applied when we use the Gaussian surface. These conditions are, for example, we choose a shape of a Gaussian surface, could be spherical, could be cylinder, could be another shape, if it make the following points included, or one or maybe two of them. Okay. So if it make, for example, it's always a good idea to choose a Gaussian surface where the electric field at every point on that Gaussian surface has equal or the same electric field. Why? Because in that case, electric field will be constant and it will go out from the integration or integral. So it makes our life easy. Okay. And there are situations that we can't find Gaussian surface, so we will simply say we can solve it using Gaussian surface or Gauss law. So let's go through one example or a few examples. Okay. So this is example 23.6. We have an insulating solid sphere. Insulating, think about like rubber ball. Okay, has a radius a. So it's that a, and a uniform volume charge density. What does it mean, uniform charge volume density? It means charge nicely distributed over its volume. And so the total charge of it, and it's positive, is equal to Q. Question asks us, calculate the magnitude of electric field outside of the sphere, somewhere located here. So the first thing is somewhere located here. The first thing is we need to write Gauss law. So this is Gauss law. This is Gauss law. Okay, what happened to the dot product? Well, let's see. Again, these lines. I don't know what's these lines. Pointer, eraser, pointer, pen. Okay. Now, let me explain this. So we need to evaluate. We need to evaluate this. We need to calculate this. What does this equal? Well, this equal to E dA cosine of the angle. Which angle? Angle between E and the dA. So where is dA? Well, dA is a small piece on a big sphere. First of all, this is Gaussian surface. Think about like a big sphere surrounding the other sphere, the smaller one. This is Gaussian surface. We call it Gaussian surface. In this case, it's a sphere. So if this is dA, where is the direction of dA? Well, it goes that way. This is dA. Where is the direction of the electric field? If this is positive, of course, electric field here will be that direction. So what's the angle between them? 0. So this is simply is equal to E multiplied by dA. Doesn't matter if you take dA here, or here, or here, or anywhere, the angle between dA, all these dAs, and electric field still is equal to 0, which means our life will be very easy because our integration will be very easy. And also E is constant, so electric field here, 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 they all constant because they all have the same distance from the sphere, which means our integration will be easy because it's going to simply go out. E will go out from the integral. Okay, so it's integration of dA. Now, how much charge you have inside the Gaussian surface? Well, we have everything inside it. We have everything, so Q in is equal to Q. Okay, we know that, we know this. What's integration of dA? So if you have a sphere, if you add all the small pieces on a sphere, surface element, all the small areas of the sphere, what do you get? You will get the surface area of a sphere. What surface area of a sphere is 4 pi r square. 4 pi r square. So E is simply equal to that equation. Look at this nice result. Isn't this similar to an electric field outside a point charge? The answer is yes, of course, which means the electric field outside the point charge is exactly the same equation as electric field outside the sphere. Okay, so this is very good result, and it's easy to people to memorize it. Okay. But it's important, this is only true for outside. The point is located outside. Because we have the second part of the problem, ask us the following. Now, B, find the magnitude of the electric field at a point inside the sphere. Well, this is inside the sphere. So we're going to make a Gaussian sphere, this Gaussian sphere inside. The first thing we notice is only charge inside the Gaussian sphere is included in the problem. And that charge, the Q in, it's actually smaller than the big Q, right? Because we are inside. It's smaller. So how we could find this? Well, we're going to use the idea of volume density. We will find this very easy. We will simply find the idea of volume because it's the same material. So big volume, I'm sorry, the rho. So we will get the rho. The rho for the big sphere is equal to the rho for the small sphere, right? For the inner one, because the same material. Now, Q inside isn't equal to the rho multiplied by the volume of the smaller sphere. See, there is a prime here. I mean, this is for the small one. It's simply definition of rho, right? Rho, so let me write it here. Rho isn't equal to Q inside. So now we are speaking about the Gaussian surface, the small one, divided by V prime. And what's the volume of the sphere isn't equal to 4 divided by 3 pi r cubic. Remember, I use r cubic, I didn't use a, because we are speaking about the Gaussian sphere. Okay, so very simple. Now we bring this and we plug it inside the right hand side of the equation. Left hand side of the equation is similar to the previous case. This is easy peasy. Okay, so when you do this, when you substitute Q in into Gaussian surface, we simply have this equation. But we haven't done yet because rho is not given. But rho, can I write it as Q, big Q, because rho is a density, isn't equal to the total Q divided by the total volume of the big sphere, which is 4 divided by 3. So this is simply a rho. Rho is equal also to the big Q divided by big volume, which equals to Q divided by 4 divided by 3 pi a cubic. Here, rho, this is for the small, this is for the Gaussian surface. Okay, so you do that and look at this answer. Again, it's not easy to memorize this answer, but there is something unique about that answer. Let me explain. Let me a little bit clean up this mess. I just need to talk about the last two equations, okay? And I want to explain this graph. Go back here, pointers, pen. So this is our sphere. Okay. We have electric field and we have a distance. First, let's talk about outside. Well, outside, this is the equation outside. Remember, it is 1 divided by r squared. So it's going to go a little bit curved like this, right? Because this is the equation that need to be used for outside. But for inside, it's a constant multiplied by r. So this is kind of similar to y is equal to slope multiplied by x. Our y is electric field, our x is r, and our slope is just this constant. So look at it, it's linear, which means, again, this line, that's fine. Okay, so which means electric field increasing 0 exactly in the middle, 0, and then increase, maximum value is exactly at the surface. and then decrease, decrease, decrease. Of course, if you are very far, this is going to be 0, right? Because if you are very far, this value will, I mean, q divided by r squared will simply approach 0. Okay. Second example. Here, we try to find electric field at a distance d. We will find electric field at a distance, at a distance r from a line of positive charge. It talks about this, okay? This is the line of infinite length. It's very, very long. Of course, here is just a small piece shown. Infinite length and constant charge per unit length. So this brown charged object is very long and it's one dimensional. How do I know it's one dimension? Because lambda is given. Okay, so don't think about like a rod. It has no thickness. Think about like a hair, human hair, and charged with positive. And question asks us, what's the electric field just at a distance r from it? Doesn't matter. It's from this side, the other side, doesn't matter. So what do we do here? We need Gaussian surface. This Gaussian surface is a cylinder. Why? Because if I use sphere, so let's do a terrible job here. Let me use a sphere here. That's not good because this is positive. So I know electric field is going this way. Of course, in 3 dimensions, it's going to go all the way, right? All direction, I should say. Now, you already know there is a problem because if this is electric field, this dA with electric field, the angle is 0. But what about this dA here? dA is like that. Now there is an angle. What about this dA here? What about this dA here? What about actually this dA here? dA is going downward, but electric field, there is no electric field that, which means the angle between electric field and dA keep changing. So our integration or our integral cannot be solved. It will be very difficult. We cannot do that. But what about cylinder? Cylinder make our life easy. Now cylinder, if you take a small piece of a cylinder, like it's shown here, dA is to that direction and E is to that direction. Angle between them, 0. That's good. But we have to apply Gaussian law or Gauss law. Okay. Now the first question, how many surfaces we have for a cylinder? Well, we have the top surface. So this is for the top. So this is top. We have for the bottom one. We have for the side one. So this is just equal to Q inside divided by epsilon. Okay, look at this. Is there any flux that goes through the top and the bottom one? No. There are no flux that going through the top and the bottom because electric field simply going this direction. Okay, but A for that surface, A goes like this. Angle is equal to 90, so no flux through the top part, no flux through the bottom one. What about the side? Well, this is a different story. The side, the angle is equal to 0, so it's equal to EDA cosine 0, and is equal to EDA. Now, what's the area of a cylinder? Remember, of a side cylinder is equal to 2 pi r L. Let me explain this. You have this cylinder. Remember, we are only doing the side one. So imagine you have a can of a Pepsi. You take out the top, you take out the bottom. Okay, so what do you have? You just have like a hollow cylinder, open from the top, open from the bottom. So somebody asks you, what's the area of it? So one idea is simply cut it, right? You cut this. You cut it by a scissor. So what do you have? You will have something like this. The top part will be 2 pi r, right? Which is the circumference of this circle. And the length will be, let's call it L. So what's this area now? 2 pi r L. Okay, so now we're done. In the left-hand side of the equation, we're done. Now we have a problem. It's not a problem, but we have to figure out how much charge we have inside this cylinder. Do we have the total charge? No. We only have this amount of charge that's located inside the cylinder. But we are smart. We know how to find this Q. Actually, this is the Q inside. We will use the idea of density. So that charge isn't equal to lambda multiplied by the L, by the length, assuming this is L. Yes. So L with L will cancel out. There we go. Move this parameter to the right, you simply get the answer. Okay? This is simply the answer. Now you could even do a better job. You multiply by 2, divide by 2, so this is the result. There is one more example. I'm not going through it. I nicely put my handwriting, my solution there. I want you to go through this, and if you have any question, of course, you feel free to ask me. And thank you for watching. So this is the end of chapter 23.